Hi, everyone. Welcome to the Monday seminar. Super excited to see people and to have a chance to have a conversation and to hear a talk about depth-dependent dynamics of slow slip. The formal part of the announcement is done by email, and hopefully you got that. If you didn't, I will put into the chat in a few minutes the way to sign up for the email announcements. But I'm super happy to say that, Mathilde Radiguet is joined us today from Grenoble. And she's going to talk about some interesting things that she's been doing with slow slip. Typically, we ask people to mute during the talk, but encourage you to interrupt with points of clarification. And then we have a nice time at the end for an extended discussion and question and answer period. So with nothing more from me, I will turn things over to Mathilde. Thank you very much for being here.
Hi, everyone. Thanks, Chris, for the nice introduction, and thanks for giving me the opportunity to present this work. I must say I often watch these things afterwards on YouTube, but I enjoy very much all the previous talks. So today I'm going to discuss about depth-dependent dynamics of slow slip, as can be seen by geodetic and seismic observation. And this work has been done in collaboration with a lot of people, in particular Zakaria El-Yousfi, with a PhD student in Grenoble, but also Baptiste Rousset, William Frank, Vladimir Kostoglodov, and Katarina Kazaskina from UNAM in Mexico, and also Alan Osker. So I will start by discussing a little bit an example of distribution of slow earthquake from southwest Japan, from this nice figure from Obara and Kato. And in this figure, you can see the distribution of slow earthquake. So if we go from the trench to the deeper parts, you see shallow, very low frequency earthquake and tremor quite close to the trench, and these events are detected mostly by seismic observation. And then if we go a bit deeper, we have megathrust earthquake, which can be up to magnitude 8 or more, with recurrence interval of hundreds of years, and which last a few seconds, and these are recorded by seismic and geodetic observations. If we go a bit deeper, we have these events in yellow here, which correspond to long-term SSEs with equivalent magnitude around magnitude 7, and they have recurrence intervals of several years and durations from half a year to 5 years in these regions. And these long-term SSEs are mostly observed by geodetic observation and GNSS. If we go a bit deeper, we have this band of red dots here, which corresponds to deep ETS, or episodic tremor and slip. And at that depth, things can be detected either by seismic observation, and these seismic events are tremors or low frequency earthquakes. So here I'm showing a record of tremors, and if we zoom in on a tiny part of this tremor signal, we can detect low frequency earthquake, which are tiny repeating events. At these depths, we can also sometimes have geodetic observation to constrain what is seen, but it depends a bit on the signal-to-noise ratio, so this varies depending on regions. And these deep episodic tremor and slip, which are also called short-term slow slip events, can also be detected by borehole tilt or strain meters data. So to look at it in a cross-section, we have something like this, where we have the megathrust, and down deep of the megathrust, some long-term slow slip events, and even deeper short-term SSEs, which are accompanied by seismic observation, such as tremors and low-frequency earthquake. So we have this transition from a large frictional stick slip instabilities in the seismogenic zone to intermittent slow slip that is sometimes accompanied by weak seismicity when we go deeper. And if we go even deeper, we have continuous sliding. If we now focus a little bit on this region where we observe some seismic markers, so the deep ETS zone, previous observations have also shown some variability depending on the depths. And so this paper is from, this figure is from previous work of Weck and Krieger, who showed the activity of tremor in Cascadia. And they have investigating the depth variability of tremor. And so if we look at tremors that occur up deep in the tremor zone, we see that their activity is quite episodic. And the deeper we go, if we go down deep here, their activity is more continuous and the tremor bursts are more frequent. So whatever the depths, the tremor activity is episodic and strongly clustered in time. And we assume that this tremor activity is a marker of the ongoing slow slip that it also accompanies. And with increasing depths, we see a transition from large infrequent tremor bursts to a small and frequent tremor activity if we go down deep. So if we try to come up with a kind of state of the art of this previous observation, we see that we have a transition from intermittent to quasi-continuous motion with increasing depths, which can be interpreted as this mechanical transition from frictional stick slip to viscous strip at depths. And geodetic observation is really helpful to characterize the dynamic of the long-term slow slip. And sometimes this what occurs at deeper depths in the ETS zone. And seismic data reveal the dynamic of slow slip in this deeper part of the transition zone. There are some limitations to what have been done before, and in particular, we are missing some quantitative comparison between various regions. So this sketch I'm showing you here, is it observed everywhere? And can we bring additional observation to constrain its variability across different regions? So today, we'll try to address this limitation by looking at other various subduction zones. And also, I'm going to show you that we can get additional knowledge by bringing together seismicity and geodesy to analyze in more details the slow slip dynamics. Today, we are also going to make the hypothesis that all the seismic observations associated with slow slip, such as tremors and low-frequency earthquake, are a marker of the ongoing slow slip process, and that this seismic observation can be used to infer the slow slip dynamics. So today, I will focus on two main parts. So I will try to show you how we can investigate slow slip dynamics by bringing together new observation constraints on its intermittence and its depth variability. So I will start by investigating the intermittence of slow slip activity along the Mexican subduction zone and showing you evidence for both long-term and short-term SSE activity. And in the second part, we will show how we can focus on the deeper part, the ETS part, and say something about this deep transition using low-frequency earthquake clustering across various tectonic contexts. So for this first part, we will focus on the Mexican subduction zone. So this is just an introduction figure showing you the tectonic context. The red contours show the major thrust events that occurred in this area. You can recognize here the Guerrero seismic gap, where no large earthquake have been observed for at least 1 century. And the most recent earthquakes are shown by their focal mechanisms. So we will focus in the following on the Guerrero and Oaxaca states, which are the places of the Mexican subduction zone where most large slow slip have been observed. So this is a zoom on Guerrero and Oaxaca regions. You recognize the red contours showing here the megathrust earthquake. And I'm showing in blue here the location of the regions where long-term slow slip events have been observed. So how have they been observed? They've been observed mostly by GNSS data. So I'm showing you two GNSS time series, one in blue here in the state of Guerrero and another one here in the state of Oaxaca. And this GNSS time series clearly show the activity of large slow slip events. So in Guerrero, these slow slip events have they recur about every 3 to 4 years, a bit more complex in most recent year, and they have equivalent magnitude up to 7.5. And in Oaxaca, they're a bit more frequent, every 1 to 2 years, with equivalent magnitude of around 7. Tectonic tremors have also been observed in that region, and they are located down deep of this large slow slip event region. So the contours of the tremor zone are shown here in yellow. These tremors have been detected by different methods, but in particular, I'm going to discuss today this single station tremor detection catalog made by Alan Husker from Spectrogram. So the advantage of this tremor catalog is that it's very long time. It's 10 years because it uses permanent seismic station. However, we don't have any locations, so we have catalogs for 4 stations, Arik, Plig, and Plig Yoik. So these 4 stations shown in red here. In addition to those tremor catalog, there are also some low-frequency earthquake catalog who's been performed by William Frank. And this, if we plot on the same map the location of this low-frequency earthquake, we see that we have a sweet spot of low-frequency earthquake, which is located just above the tremor zone, down deep from the larger slow slip events, and a more transient activity, which is a bit located a bit up deep in the Guerrero subduction zone. The temporal variability of this LFE activity has also been investigated by looking at recurrence interval as a function of time over the 3-year period. And this allows to detect short-term slow slip events, which are shown in red here. So these are periods of intense LFE activity that occur during that time period every 3 months. And I will show just after that this intense LFE period can be associated with a geodetic signal and correspond to short-term slow slip events which have equivalent magnitude around 6.4. In addition, this low-frequency earthquake also allows to detect during a large slow slip, which is shown in blue here, that there is an intermittence in the slow slip activity. This intermittence during large slow slip I will not discuss today. So going back to the short-term slow slip events that have been detected with this LFE activity, we can relate the signal observed by tremor here. So this is a figure showing the intensity of tremor over 3 years from 2005 to 2007, the same LFE catalog that I showed you before, and the surface displacement observed by GNSS. So what we can see is that we have a very clear slow slip signal associated with intense tremor activity during the large slow slip events. This I will not discuss more, but we also have periods of high tremor intensity, which are associated with a lot of LFE activity. But if we look like that, we cannot detect any a strong signal in the surface in the GNSS surface displacement because the displacement is too tiny. However, in 2005, we showed with William Frank that if we stack the displacement associated with all this signal, we can detect a tiny surface displacement of 1 to 2 millimeters per event. That is shown by the arrows here. And this small surface displacement, if we invert it for slip on the plate interface, it corresponds to a slip distribution of about 10 millimeters per event. And this we interpret as the occurrence of short-term slow slip events just above the tremor zone. By comparison, we can look at the long-term slow slip events that is located above, up deep, and that is associated with a much stronger surface displacement up to 15 centimeters. So to summarize, in 2005, we had this view of long-term slow slip events with a recurrence of 3 to 4 years and surface and slip about 15 centimeters, and down deep, some short-term slow slip events with recurrence interval of 2 to 3 months and equivalent magnitude of 6.4. And if we look at cross-section, these short-term SSEs, they are located down deep of the zone of the larger slow slip events. But this analysis is limited to 3 years because we had only 3 years of low-frequency earthquake catalog. So more recently, we decided to reinvestigate this with a similar study, but this time using the 10-year tremor catalog produced by Allen Husker, which is available at 4 seismic stations in both Guerrero and Oaxaca. So the idea here is to combine long-term tremor catalog with GNSS time series and to analyze both the Guerrero region and the Oaxaca region. So to do so, we start by investigating the tremor catalog. So this is the tremor duration of this as a function of time, and we clearly see that the tremor activity occurs in bursts. If we look at the cumulative number of tremors as a function of time, we can identify periods of long-term slow slip events and periods in between where we also have tremor activity. So to better see the variability, we detrend this catalog. And by detrending the catalog, we can clearly identify the episodicity and the different bursts. And we then detect all the tremor bursts by looking at the variability in the trend of this curve. So the tremor bursts are shown in gray in that figure. So we detect about 30 bursts in the right period here, so not during the large slow slip events, with an average duration of 8 days. And we then also investigate the GNSS time series. So this is a raw GNSS time series. We use a trajectory model to remove the linear trend and the seasonal variation. And so we end up with this residual GNSS time series, and we are going to focus here on the period between the large slow slip events, where we don't see any detectable surface displacement when we look by eye at the time series. And so what we do is that we decompose the GNSS time series based on the tremor time. So to do that, we focus on one tremor burst. We average the GNSS position before and after the burst. Then we compute the offset associated with the burst. And we estimate for each tremor burst the slip rate during one burst, which is the offset divided by the duration. And we do that for all the tremor bursts. So this allows us to separate this period of interlong SSE between the period of tremor activity that is shown in black and the period between tremor activity that is shown in red. So on average, the velocity is 0 because you see that if you look at the time series on the top, the time series is flat. So the average velocity is 0, but if we separate between the tremor period and the intertremor period, we see a negative slope during the tremor period with velocity, surface velocity around 30 millimeters per year, and positive tremor period, positive velocity in between the tremor period. So this corresponds to loading of the plate interface when the velocity is positive, and it corresponds to release when the velocity is negative. And to investigate the uncertainties associated with this decomposition, we perform a random shuffling in time of the tectonic tremor time. So this gives us uncertainty. So this is the velocity for the tectonic tremor rate or intertectonic tremor rates for the random shuffling. And we see that the actual velocity that we detect for the true tremor time are really outside this uncertainty range, which gives us confidence that our results are robust. Yes, Joanne, you have a question?
Yes, sorry. So you mentioned that the average duration of the tremor bursts was 8 hours, but you are likely
8 days, sorry, 8 days.
8 days. Oh, okay. Never mind. Sorry.
Yeah.
Okay.
Maybe I said hours, but it's days. So this gives us an idea of the uncertainty associated with our velocity estimate. And the next step is to do that for all the stations that we have available. And so we on the map, I'm showing the black arrow here, so the velocity during the tremor time for all the GPS stations in the area. So this is the black arrow on the map. And then we invert these displacements. So they are very coherent. So this is a second, this also tells us that our results are quite robust. And so when we invert, we find a slip patch that is located just above the tremor zone that is shown here just below. So this is for Guerrero. So for Guerrero, we retrieved the location of the short-term SSEs that had been identified in this study in 2005 using the low-frequency earthquake. And in Oaxaca, we performed the same, and we retrieve also a region of short-term slow slip events at the same location as the tremor zone, and this had never been investigated before. This is the first time that these short-term SSEs have been observed in Oaxaca. So we see that we have faster sleep rates during tremor time, both in Guerrero and in Oaxaca. And the sleep that we retrieve by inversion is collocated with the tremor. So we are able to observe over this 10-year period short-term slow sleep, both in Guerrero and Oaxaca. And if we combine the result on the single map, what we are showing here is up deep, we have the location of the long-term slow sleep events that have been investigated by various studies. And down deep, we have both in Guerrero and Oaxaca, the location of the short-term SSEs that are more frequent and shorter and have shorter duration. So in average, we find recurrence interval around 40 days and duration of 8 to 9 days for these events. So next, I would like to investigate a bit more the activity of the tremor and a low-frequency earthquake within this region of short-term slow sleep events. And I will do that not only for the region of Mexico, but also for other subduction zone and also one strike slip fault. So if we look at the activity of low-frequency earthquake in the transition zone, as I said in the introduction, and I'm showing here the example of Nankai. So in this map, I'm showing the low-frequency earthquake activity in Nankai. So each dot here represents an LFE family, and they are color-coded by depth. So if we look at the activity of a family at depth, here I'm showing the number of events as a function of time. You see that the activity is very continuous. And if we look at the activity of a family that is more shallow, its activity is more intermittent. This is what we see for this 10-year catalog. So the objective here will be to use this LFE activity to analyze the dynamic of slow sleep in this rheological transition from intermittent frictional stick slip to continuous viscous sweep in various tectonic contexts. And we will do that by looking at four different regions, 3 subduction zones, Nankai, Guerrero, and Cascadia. And in each case, we use existing LFE catalog from Cato, Sweet, and Frank in Guerrero. And we also include in that study the region of Parkfield, where we use the catalog of David Shelley. And in all regions, well, we are going to bin the LFE catalogs across depths. So we are going to sample from the up deep, from down deep of this transition zone. In each case, we see that the depth-dependent behavior is always observed. So in each of our catalog, we see a variability between the up-deep region that is more continuous, that is more episodic, and the down-deep region that is more continuous. And what we want to do is to systematically estimate the duration and the recurrence of the LFE burst that we detect in this various regions. And we want to do that in a systematic manner so that we can use the same methodology for all regions, and we want to find a robust methodology to analyze all regions. So to do that, we start by looking at the LFE activity time series as a function of time. And I'm showing here 2 families, an up-deep family and a down-deep family. And we perform the autocorrelation of this catalog. And if we zoom in on the central parts, we are going to use the width of the central peak to give an estimate of the duration. So in this case, for example, we have a duration of 1 day for the down dip family and a duration of 11 days for the up dip family. So this duration is given by the width of the autocorrelation peak, and it gives us the average duration of an LFE burst in that region. To get an estimate of the recurrence, we want to investigate the appearance of a secondary peak in this autocorrelation function. And this secondary peak can be better retrieved by looking at the Fourier transform of the autocorrelation. And we pick the frequency at which the energy starts to decrease. So in this case, for example, this is 34 days for the down dip family and 124 days for the up dip family.
Mathilde, it's Chris. Sorry to interrupt.
Sure.
Can you go back and remind us, like for Parkfield or really any of the places?
Yes.
How do you decide which is up and down dip? How do you choose the depth?
So basically we investigate the behavior as a function of depth for all the regions. Okay, so for Parkfield, this is trivial. We just take the depths. For the other region, what we do is that we project the LFE on the plate interface.
Mhm.
And we assume that they all occur on the plate interface. So we have some uncertainty on the location, but we project them on the plate interface. And then we look at their depth variability. So when we look at that, this is the bins of the number of family per bins as a function of depth.
And like at Parkfield, how did you choose the depth between to distinguish them? Up dip and down dip?
Well, this is just, we look at the maximum and the minimum location, and then we take 10 bins across so this is just from the catalog itself. So the up dip is just the minimum depth, and the down dip is just the maximum depth.
Gotcha.
Does it make sense?
Yeah, thank you.
So we do that for this evaluation of duration and recurrence for all depth range and all regions. And we end up with this kind of plot where we can see the duration as a function of depth and the recurrence as a function of depth for all regions and all depth range. And so we observe a decrease in the duration and the recurrence with increasing depth. This is expected. This is what has been observed in previous study. But we can make this plot and give a systematic and coherent estimation of this variability. And the question now is, well, how can we interpret that, and how can we reconcile the observations of these various tectonic contexts, and can we explain, can we say something about the influence of the loading velocity or the temperature? These are the two factors that we think can explain somehow the variability observed. So we come up with a very simple model of episodic slip in the transition zone. So this is the simplest model you can think of, where we assume that the slip is the succession of stick and slip phases. And we compare the cumulative slip for this case of stick slip and a case where we have a continuous slip at the convergence velocity. So if we assume similar budgets for intermittent and continuous sliding, we can say that the recurrence, which can vary with depth, times the loading velocity is equal to the duration times, the event sleep rate. And this sleep rate during events, it can thus be given by the ratio between the recurrence interval and the duration times the loading velocity. So we see that the ratio between recurrence and duration is something that is quite important. So we can look at how the recurrence varies with respect to the duration for all the regions. So we make these plots of recurrence versus duration for all the regions. And we see that at first order, we can make, they vary linearly for different depths, and we can estimate the trend of this recurrence duration plot for all the regions. And if we plot the ratio of recurrence versus duration times the loading velocity, which correspond to what we call the sleep rate here, as a function of depth, well, we observe that we have very similar sleep rates for all the regions. And this is about 1 centimeter per day. So as a conclusion, we can say that the ratio between recurrence and duration is almost constant along this transition zone. And it corresponds to a sleep rate around 1 centimeter per day. And by doing so, we normalized by the loading velocity. And this allows us to explain part of the variability that we observed in the recurrence. However, we see that we still have a large range of depths, which are very different depending on the region. And to explain this variability, we can look at the effect of the temperature. So this time, we use various geotherms that have been published in the literature for all these regions. So in green here, we have Parkfield, which has a very different geotherm from the 3 other regions, which are the subduction zone. And we show in bold here the regions where we observe the LFE activity. And so we can compare this figure of sleep rate as a function of depth by a figure where we now show the sleep rate as a function of the temperature. And we see that the temperature range is much more limited with respect to the depth or pressure range that we observed previously. And across all tectonic contexts, we observe our LFE on a temperature range from 400 to 600 degrees C. And going from this depth to the temperature allows to reconcile in particular the observation in the strike slip context with the observation in the subduction context. And in the small inset here, I'm comparing the sleep rates during the slow sleep, which is, as I said here, estimated to about 1 centimeter per day. So this is quite similar, and we can compare it with the loading rates and the earthquake rate, so which are several order of magnitude higher and lower. So in conclusion for this part, we have seen that the LFE activity can be used to estimate the timescale of slow sleep in the transition zone across 4 plate boundaries. We observe a decrease in the recurrence and the duration of slow sleep with increasing depths. And we see that the ratio between recurrence and duration is almost constant. And this tells us that the average slow sleep rate is 1 centimeter per day with this simple model of episodic sleep. Temperature is the main parameter that controls the intermittence and the strength in the transition zone. And so we hope that this study provides some observational constraint on the dynamics of this region, where there is a mix between brittle frictional deformation and viscous creep at greater depths. And some general conclusion for this work. So the objective today was to show you how we can investigate slow slip dynamics and bring new observational constraints on the intermittence and its depth variability across various regions. So I started by showing you some evidence of long-term slow slip and short-term slow slip at greater depths in the Mexican subduction zone, and in particular, how we have been able to show the existence of short-term slow slip events, both in Guerrero and Oaxaca, by joining together geodetic and seismic observation over this 10-year catalog. And we were able to show this short-term slow slip with a recurrence interval of about 40 days and duration of 8 to 9 days. They produce very tiny surface displacements, around 1 millimeter. So we need a combined analysis, and we have to stack GNSS data to be able to detect the associated surface displacement. And focusing on the deeper parts of the ETS zone, I've shown that we can use the episodic activity of LFE to show, to monitor the activity and the variability across depths. And we see that both recurrence and duration of slow slip decrease with depth in 4 different tectonic contexts. That temperature is the main controlling factor of this intermittence, and that the ratio of the recurrence and duration is almost constant with this simple model of episodic slip. Thank you. I'll be happy to take some questions.
Thank you very much. Wow, what a nice talk. And yes, please unmute or turn your camera on. Join me. Thank you, Mathilde. Really interesting talk.